Welcome back to trigonometry. Today we're going to start talking a little bit about some identities. We'll cover these in way more depth, more identities and more in depth in the future, in a future unit. But right now we're going to today talk about the Pythagorean identities and the quotient identities. And talk a little bit about how to use them to help solve some problems and so forth. Okay, but before I derive these identities, that's going to be my plan of attack, is to derive the identities and then show you some useful situations and stuff. But before I do, I wanted to recap something about the trig functions, and you'll find this information useful as we start talking about identities and so forth. We had before dealt with looking at right triangles and then trying to solve right triangles, trying to decide on lengths, like trying to figure out the lengths of sides and trying to figure out the different trig ratios and so forth. Like for this right triangle here, let's label this direction would be your x values, this direction would be your y values if this were situated on xy axis grid, like with this being the origin right here. Angle here is going to be our theta, and the hypotenuse is r. Now we talked about the fact that r is found by doing the square root of x squared plus y squared, and that comes from Pythagorean theorem, or you can also think about the distance formula, trying to find the distance between 2 points. It's basically using the Pythagorean theorem to do that. And our r here is thought to be non-negative. Now when we talked about sine of theta, let's switch colors. When we talked about sine of theta equaling y over r, opposite over hypotenuse, there's some things that we have to consider here. The r, being the hypotenuse, is the longest side on that right triangle. So the y is smaller than the r. So whatever, if y is positive, and then your r is always going to be positive, you have a smaller number over a larger number, that's always going to give you a proper fraction. So that sine of theta is going to be less than or equal to 1. If y and r could be equal, and that could give you 1. Or if y is smaller than r, then that's going to give you something that's less than 1. If y is 0, you could have 0 over something, which would be 0. Or if let's say this is a reference triangle situated in a different quadrant, let's say it's down in quadrants 3 or 4 and your y is negative, well then you'd have a negative over a positive, and the absolute value of y would still be smaller or equal to r, so then that would put this being greater than or equal to negative 1. It's just all has to do with the way the y and r are related, like what those numerical values could possibly be. Y could equal r, which would give you 1, or y is going to be less than r in some way, which would give you this proper type fraction, which positive fraction would be less than 1, and the negative fraction would be greater than negative 1. So that's for your sine. And the same thing happens with cosine. Cosine of theta, we talked about being x over r. Well, for the same reasons that sine of theta is greater than or equal to negative 1, less than or equal to positive 1, cosine theta is as well. Now if you look at their reciprocals, cosecant of theta, that's r over y. That's the reciprocal of sine theta. And assuming y isn't 0. If it is 0, then you got something that's undefined, which that happens too. But you're talking about reciprocal here. So where sine is from negative 1 to 1, cosecant of theta is going to be either bigger 1 or higher, or negative 1 or lower. So it's going to be greater than equal, or greater than equal to 1, or it can be less than equal to negative 1. And then same thing happens when you're dealing over here, like with the cosine, it's reciprocal. You got secant of theta. That's r over x. Well, instead of being from negative 1 to 1, basically you could say, well, the absolute value is going to be greater than equal to 1. So it can fall, it can be 1 or higher, or it can be negative 1 or lower. And then you got the lovely tangent of theta. Tangent of theta we talked about being y over x, of course assuming that x isn't 0. If x is 0, then it's undefined, and that's where you're going to get something called an asymptote when we talk about graphing these later. But for now, tangent of theta equals y over x. Well, y can be smaller than x, y can be equal to x, y can be bigger than x. So your tangent theta there can be any real number. And the same thing goes for cotangent theta, which is the reciprocal of tangent. X can be smaller than y, x can be equal to y, x can be greater than y. Assuming y is not 0. So cotangent theta can be any real number. So these are just some considerations to make. So, like if you're doing a problem and they tell you, hey, sine theta equals 2, it's like, well, I know that can't be true because sine theta can't equal anything bigger than 1 or less than negative 1. We're looking at our range here, our ranges. Knowing these ranges can help you to see if a problem's doable or not. All right, so that's just something to keep in mind, as we do all of our problems. Okay, now moving on to these identities, the Pythagorean identities first. Okay, I'm going to keep reusing all this info, all these different statements that we've been making. We know that x squared plus y squared equals r squared. You're going to be sick of hearing that by the time this course is over, but we know that. We can do a little algebraic manipulation and actually start playing around with this and develop some identities that are very useful when solving problems. For instance, we could take this right now and we could divide everything through by r squared, assuming r isn't 0. So we got x over r squared plus y over r squared equals 1. But wait a minute. Cosine theta is x over r. Oh my goodness. So we've got cosine theta squared plus, and then sine theta is y over r. So we've got sine theta squared equals 1. Or another way to write this, perfectly legal way to write this too, would be to say cosine squared theta. So cosine of theta squared can also be written cosine squared theta. Those two mean the same thing. Plus sine squared theta equals 1. And there is one of our identities. Pretty cool, eh? Well, be familiar with the fact that, that this is true. And also be aware that cosine squared theta can equal 1 minus sine squared theta, or sine squared theta can equal 1 minus cosine squared theta. It's just a matter of subtracting either cosine squared theta from both sides or sine squared theta from both sides. So this equal sign means we can do a little manipulating. We could subtract the same thing from both sides and just make the identity look a little different. Or, okay, going back, x squared plus y squared equals r squared. Let's get a little crazy. And instead of dividing both sides by r squared, how about we divide both sides by x squared? Let me know if it's getting too crazy for you. We can have some fun here. Let's see. We're going to have 1 plus y over x squared equals r over x squared. The 1 part's the easy part. But y over x, remember what y over x is? Now we're talking about those reciprocals. So you got the instead and r over x stuff is getting a little crazier. Y over x we know to be tangent theta. So we have tangent theta squared. And then r over x again we know to be secant theta. Coolness. And again, you could write this instead as 1 plus tangent squared theta equals secant squared theta. And yet, there is another identity. I love identities. Identities are one of my favorite things in trig. They really are. So, 2 down. Let's do one more. Let's see. Can we get really crazy and divide through by y squared? X squared plus y squared equals r squared, because we haven't done that yet. Because we divided through this one by r squared, divided this one through by x squared. Let's do y squared. Alright, x squared over y squared plus y squared over y squared. It's an equation, it's an equal sign, so we're legally allowed to do this. Okay, so we got x over y squared plus 1 equals r over y squared. Alright, let's make some substitutions here. Because we know x over y, it doesn't have to just be written x over y. We know we could say cotangent theta squared plus 1 equals, and then r over y is cosecant theta. That's squared. So we can say cotangent squared theta plus 1 equals cosecant squared of theta. And there is a third, the third of the Pythagorean identities. Pretty cool. That's your Pythagorean identities. And then a couple more I can address was the quotient identities. We're on a roll here, so let's go ahead and knock these out too. Let's see where they come from. Quotient identities. If you take sine of theta over cosine theta, you do that ratio. Sine theta is y over r, cosine theta is x over r. It's the same thing as saying y over r divided by x over r. Well, that's the same thing as saying y over r times r over x. The r's reduced down to 1, you're left with y over x. Y over x is the same thing as tangent theta. Oh, look at that. Tangent of theta equals sine of theta over cosine theta. There's one of your quotient identities. And since cotangent of theta is 1 over tangent, we can go ahead and say cotangent of theta is 1 over this, the reciprocal of this, which will lead to cosine theta over sine theta. 2 more identities. Nice and useful. Okay. So let's start playing with some of these identities a little bit. Let's use them to help us to find some function values. We found function values before by sketching the right triangles on the grid and looking at the sine, cosine, tangent ratios, and then deciding on the signs, SIGNs, based on what quadrant we were in. And I told you guys to think about a smart trig class. In quadrant 1, all of your trig ratios are positive. In quadrant 2, smart sine, your SINE, that's positive, the others are negative. Quadrant 3, trig, T, tangent, tangent's positive, and then you got the others were negative. And then class, a smart trig class, cosine's positive, the others are negative. So you got to think about what quadrant you're in to look at your signs. So that's something to keep in mind. And then also keep in mind that they're reciprocals. Like if you're dealing with cosine, if cosine's negative, secant's going to be negative too. If sine's negative, cosine's going to be negative. If tangent's negative, cotangent's going to be negative. So whatever sign the one has, its reciprocal is going to have the same SIGN. And it all depends on what quadrant you're in. But we can also use these identities to help us to solve some right triangle problems too. You don't just have to, you can draw the right triangles and sketch them out and see what you get, but the identities can be useful as well. So I wanted to go ahead and do a couple of examples where we have to use identities to help figure these out. Okay, let's say that we are given that the sine of theta is negative square root of 2 over 3. And that the cosine of theta is greater than 0. So in other words, it's positive. Alright, if you think about your grid for a second, quadrant 1, sine, cosine, and tangent are all positive. So it can't be there because sine's negative. Quadrant 2, smart, sine is positive, cosine, tangent negative. Quadrant 3, tangent's positive, the other two are negative, but here cosine has to be positive, sine has to be negative. Quadrant 4, C, cosine's positive, the other's negative. So this must be in quadrant 4, where you have positive cosine and the others are negative. That's the thought here. Okay, and let's say we want to find cosine theta and tangent theta. And of course, once you find all of those, you can easily find the reciprocals. Okay, let's start with the fact that sine squared of theta plus cosine squared theta equals 1. That's one of the identities we derived a little bit ago. Well, we know sine here is negative square root of 2 over 3. So that squared plus cosine squared theta equals 1. Well, if we square this, we're going to end up with positive 2 ninths. So 2 ninths plus cosine squared theta equals 1. So cosine squared theta must equal 7 ninths, because 9 ninths minus 2 ninths will give you 7 ninths. So to get cosine theta, you got plus or minus the square root of 7 ninths. So plus or minus square root of 7 over 3. Now we know, though, that cosine theta is greater than 0. It's positive. So we must take the positive root here in order to make this work. So cosine theta must equal positive square root of 7 over 3. So there's one of our answers. Now it also wanted us to find tangent of theta. But remember, tan of theta, we now know to be sine theta over cosine theta. Use that identity, that quotient identity. So tan theta equals, well, sine theta was negative square root of 2 over 3. Cosine theta was square root of 7 over 3. Start reducing, the 3's will reduce out. You'll have negative square root of 2 over square root of 7. Then go ahead and rationalize the denominator. Multiply out top and bottom by square root of 7. You're going to end up with negative square root of 14 over plain old 7. And there's your tangent. But rather than draw the right triangle and try to solve it, we used identities to find the cosine and tangent. If you really wanted to, you could draw the right triangle and work with that. Like you could have said, okay, I know I'm in quadrant 4, so when I do my reference triangle here, sine of theta, you got your opposite over hypotenuse, so you must have negative square root of 2 here, you must have 3 here. And you could have used, the fact that this squared plus that squared equals that squared. So you got 9 minus 2 sevenths. This would be square root of 7. It's positive x-axis. And then you could have gone from there and gotten your values too, like cosine adjacent over hypotenuse gives you this. Tangent opposite over adjacent gives you this. Rationalize your denominator. And you'd get the same values. But the point is to show you that there's more than one way to do some of these problems. You can do your right triangle and find your ratios, or you can use the identities. Alright, let's do one more of those. Those are a lot of fun. Let's see here. Let's do one more. Let's say that you're given that the cotangent is negative 7 over 24. Oops, got to write theta. Oh. And theta is in quadrant 2. Okay, so like if you're sketching this must be your theta right here. But you can always draw a reference triangle and work with that. Alright, they want us to find the sine and the cosine. Find sine theta and cosine theta. Heck, if we know that the cotangent is negative 7 over 24, then the tangent must be negative 24 over 7. I don't know if quite yet. I have to think about this. Are we going to use that? Let's see here. We know our cotangent, and we're trying to find sine and cosine. We've got some different identities. We know cotangent equals cosine over sine. But the problem there is that if we can't say that the cosine is negative 7 and that the sine is 24, because that's out of our range for one thing. And we can't really say for sure yet what our cosine and sine were. It's probably like negative 7 over something and 24 over something, but we don't know what that something is. So we got to be really careful here. We do have that identity that says 1 plus cotangent squared theta equals cosecant squared theta. I wonder if that would do us any good. Because cosecant is the same thing as 1 over sine. So if we find the cosecant, we can find the sine. So let's try that. Let's see here. If we got 1 plus negative 7 over 24 squared equals cosecant squared theta. So 1 plus 49 over, and then 24 squared is 576 equals cosecant squared theta. 576 plus the 49, 625. 625 over 576 equals cosecant squared theta. Now cosecant is the same thing as 1 over sine. Now in quadrant 2, a smart trig class. In quadrant 2, smart, sine. Sine is positive. So if cosecant's 1 over sine, then in quadrant 2 the cosecant must be positive. So when we go to do the square root of both sides to get what cosecant equals, we can focus on the positive square root because of the quadrant we're in. We're in quadrant 2, where cosecant must be positive. So we're going to have the positive square root of 625 over square root of 576. Let's see, square root of 625 we know to be 25. And then for 576, we know that to be 24. Square root of 576 to be 24. So if cosecant is 25 over 24, necessarily sine must be 24 over 25. Good to know. Well, one down, one more to go. We still got to figure out what cosine's going to be. But hey, we figured out what sine is. Let's see here. We do have the identity that, sine squared plus cosine squared equals 1. Well, cosine squared theta is going to equal 1 minus sine squared theta. So cosine squared theta can equal 1 minus our 24/25 squared. Eek. So cosine squared theta can equal 1 minus 576 over 625. So cosine squared theta is going to equal 625 minus that. You're going to get 49 over 625. But to get cosine, we got to do a square root here. To solve that, you got plus or minus the square root of 49 over 625. So plus or minus 7 over 25. But since we are in quadrant 2, a smart trig class, quadrant 2, smart, sine is positive, cosine would necessarily be the negative one. So cosine theta equals negative 7/25. Trying to circle that. My pen didn't catch up. This is a 7 right here. Negative 7/25. So there's some examples of some problems that you can do using Pythagorean identities, but you still have to be aware of what's going on in these quadrants. You still have to be aware about all being positive in quadrant 1, sine and cosecant being positive in quadrant 2, tangent, cotangent being positive in quadrant 3, and then cosine and secant being positive in quadrant 4. And when I say those are positive, it means all the others are negative. So you still have to take that into account. Like right here, you're supposed to do plus or minus the square root when you're solving a square equation. But we only take one of those because of what quadrant we're in. So that's one way to handle this. Okay. So that's enough with the trig identities for now. We're going to have more fun with trig function values in a future podcast, but I guess we'll sign off for now for this one. Thank you for joining us.